So today's talk is going to be about a new type of quantum advantage experiment where we have certain desirable properties that were lacking in the past quantum advantage demonstrations that we have seen so far. So it's about peaked quantum advantage uh, with some properties of QEC. We will unpack these words and phrases as the talk goes on. But before that, this is joint work with my friends and collaborators from different places, Abhinav, Bill, Dominic, and Mike. But before I talk about the nitty-gritties of quantum advantage, let me start with a motivating question. Let me ask why we should care about experimental quantum advantage in the first place. The reason to care comes from Charles and Turing and the Charles-Turing thesis, which says that any computer can be efficiently simulated by a classical Turing machine. One way to think about experimental quantum advantage is that these are experimental tests of violations to the extended Charles-Turing thesis. And the motivation is to efficiently perform any task that would take a classical Turing machine exponential time. And a near-term demonstration of something like this is exactly what experimental quantum advantage is trying to get at. And the very interesting point here is numerous quantum advantage claims have already been made. The Google had the ball rolling in 2019 with the random circuit sampling experiment. But since then, there have been many other claims, USTC, Xanadu, Google's Willow chip, and a bunch of other things. And we are already seeing these experiments in practice, like I said, but there's an obvious challenge. And what's the challenge? So say Google claims that they have a quantum computer that takes 10 to the 27 years to maybe simulate, they have a quantum computer that performs some task such that a classical computer takes 10 to the 27 years to simulate the same task. So that's the claim. But there's a retort that Scott had in his blog, for instance. And the retort is, yeah, maybe classically performing the same task takes 10 to the 27 years. But verifying that the output of the quantum computation was correct in the first place, that also takes 10 to the 27 years. So verification is as bad as full classical simulation. But why care about classical verification in the first? Like, why do we care about the fact that verification is as bad as simulation? Why is that a bottleneck? Well, there are many cryptographic applications to these quantum advantage experiments, like certified randomness, digital signatures, bit commitments, and which raise a fascinating possibility that maybe quantum computers can themselves solve a problem that quantum computers will have created. Problem being, say, lack of any secure cryptography. If we have fault-tolerant quantum computers, the persistent scare or the persistent fear is that maybe they will break all types of secure cryptography. So these quantum advantage experiments can pave the way for a quantum secure cryptography using first principles of quantum mechanics. So there are all these applications, but there's one caveat. So there's one reason many of these schemes are not practical and haven't been widely implemented yet. What's the reason? It's because verification is too fast. And like I said, verification is as hard as simulating the entire system classically. So let me stop here for a few seconds. Did the motivation or why we should care about verification, did all these things make sense? Any questions for the intro?
So far, so good.
Okay. Okay. So this is why we should care about verification. So what do? Well, we propose a different type of quantum advantage experiment. Like I said, we propose hidden code sampling. So where verification is
there's
not.
a question, Soumik. Sorry to interrupt you.
Yes, yes.
So when we say like verification is also like difficult, do we
Yes.
know that that there exists no classical algorithm, randomized algorithm that actually is efficient? Like, do we know that for sure? For which that we need to know quantum?
No, we don't know that for sure in the sense that there's no unconditional proof, but there can be some conditional statements that we can make using complexity theory about verification. Like we can say that assuming this particular conjecture is true, at least verifying these like random circuit sampling based demonstrations, I call this like the like V1 of quantum advantage. So verifying those experiments is classically hard.
Okay. I mean, like, as with some other cases of like there in future there might be some classical algorithm, or like is it like complexity theoretically
It's unlikely that I mean, you cannot rule out.
Yeah.
Okay.
Like assuming a conjecture is true, like things can be ruled out. But yeah, the conjecture might be false, but it's unlikely. Yes.
So Soumik, I wanted to ask because we interrupted you. I thought I might ask you this small question. So with cross entropy benchmarking, like these measures, like which people were using to verify, random circuit sampling. So what is the status with those? Like for instance,
Yes,
XCB. Can you?
So they're inefficient. They are not polynomial time. And assuming certain conjectures are true, you can say that there's no classical method that gives you like polytime, like time complexity for these these benchmarks.
Mhm.
Like we can rule out any like we can rule out the like we can put a time lower bound on these benchmarks, assuming say some non-standard complexity conjecture. For instance, like Scott has a paper where he ties the complexity of like these cross entropy benchmarks to the complexity of one other task called X quath, and that is and the task is computing the probability, like the path integral of like a particular branch of the wave function of the state produced by the random circuit, and it's believed that this task is hard.
Okay. Although we are typically dealing with quantum computers that are of small size, right? So because we are dealing with quantum supremacy, so it will be like say 100 qubits or something like that. So even if the scaling in the exponential is like not too large, should be okay, I guess. Right?
It should be okay. Yes. At least for like 70-80 qubits, it should be fine. I think the problem comes when we have like 100 qubits or more. I'll go into this in the very next slides.
Right. Okay.
Any more questions? Okay, so what we do is we propose a new quantum advantage scheme where verification is much faster than simulation. In fact, the ratio between these two times can be exponentially large for our scheme. And our scheme does not have
a quick question. Just to maybe get like some intuition before. So if this verification is done faster than simulation, what is the hardness roughly based on? Should I think of it it's based on some cryptographic hardness or some complexity theoretic hardness, or how should I think about?
Right now it's kind of like a mix of both. I think it will be clear when I tell you the precise scheme. So I guess right now we don't have any like concrete hardness conjecture. It's a mix of say complexity theory, cryptography, and some heuristics.
Okay, I see. Thank you.
But yeah, like making it concrete is like a future direction.
Yeah, thanks.
And so like one other feature of our scheme is that it doesn't require full fault tolerance. So it's reasonable, very reasonable that it could be implemented in the short term. So before I delve into what our scheme is, let's do a brief recap of what previous schemes were. V1 of quantum advantage, like I said. So the schemes all worked in a very similar way. So you had maybe a 2D lattice of qubits. You had nearest neighbor gates and say maybe D layers. And you picked those gates randomly. And you start with some input state, like some fixed input state, say all zeros. You apply this random circuit that you pick by randomly picking the gates. And then you measure all qubits in the standard basis. So you're basically sampling from the probability distribution that's produced by this fixed state and a circuit applied to this fixed state. So because of the very nature of this task, this is quantumly easy, but there is strong evidence that this task is classically hard. And it has now been implemented. Google started with 53 qubits and depth 20, then followed it up with 60 qubits, then 105 qubits. And I think this is the state of the art, 105 qubits. And so how do we verify these experiments? So one major problem, or maybe not a problem per se, one major feature of these sampling experiments is that the output distribution produced by random circuits is extremely flat. And so this flatness is very crucial to proving hardness properties. But this flatness is also why methods like linear cross entropy, the methods that we use to verify these experiments, these fundamentally require full simulation of the entire experiment all over again. Why? Because we basically want to compute output probabilities when we are verifying by these methods. And if the distribution is too flat, the output probabilities are all kind of like equiprobable. So we really need to like resolve them to very small differences, and you really need to like kind of simulate the entire circuit with very high precision to get that resolution. And for instance, the fact that simulation and verification kind of, there's like no gap between these two timescales is very apparent in the brand new experiments. Like Google's 105 qubit depth 40 experiment can no longer be verified. It's no longer humanly possible to verify this. So what Google did was they did some cross-entropy benchmarking on a much smaller system and then extrapolated those scores for their 105 qubit device. But the actual device output wasn't verified. And so that's a problem. And ideally, we would want to design a new experiment where classical hardness is preserved. But maybe verification is easy. So how can verification be easy? Well, maybe we have some output distribution which is extremely peaked on one outcome. So say the verifier knows the outcome from beforehand, but the adversary who's running the circuit doesn't. And so when the verifier sees samples from the quantum computer, even if the samples are adversarial, the verifier would be able to detect whether the right peak comes up with high frequency in those samples. And if that's the case, then the verifier certifies that the samples came from the right distribution. And if that's not the case, they reject the samples. So that's like a very trivial way to verify any peaked distribution, where you know the peak from before. And maybe we want something like this. And like I said, we would use this large probability to verify the experiment. Did this make sense? Yeah. So if there are no questions, let me proceed. The main problem, though, is that so these are like two desirable features, like a wish list of features that we want. We want classical hardness of sampling. We can't sacrifice that, of course, because this is like a quantum advantage experiment. We also want efficient verification using this like peakedness problem. here's the problem. So how do we generate circuits which satisfy both of these features? And we also want the scheme to be as NISQ friendly as possible. Because if not, then note that there's like a trivial way to design peaked circuits. Like you can just run Shor's algorithm. So any quantum algorithm that succeeds will have to be peaked with very high probability. It has to be peaked on the correct answer. And so that's how you basically verify that you factored correctly. But that's like, that is exactly something that we don't want to do, or we don't have the capabilities of doing with near-term hardware. The entire point of quantum advantage, as I was pointing to in the beginning, is to like generate some like do something with quantum computers, something non-trivial, but do it in the near term with the hardware that we already have. And the hardware that we have cannot run short circuit. So how can we generate like NISQ-friendly peaked circuits? So there's some evidence that Scott gave that they can be generated by maybe random gates. So if you have like a random circuit, it won't be peaked most of the time. The output will be pretty flat. But there will be a negligible fraction of instances where the output will actually be peaked. And maybe you can use post-selection to find out those instances. Or maybe you can use some gradient descent based method using machine learning to kind of like search for, like you have a cost landscape, like the landscape of all circuits, and you kind of use a gradient descent method to search for, say, circuits which are peaked. But this is like an exponentially complex task, and gradient descent has no guarantee of converge to the right answer. So these are not two satisfactory solutions. What do we do here? Our main contribution is that we use error correction to efficiently generate circuits that are peaked, that are conditionally peaked, but I'll come into the meaning of this phrase later. The verification node for us is still inefficient, but the ratio between simulation time and verification time is exponentially large. So that's our main contribution. Any questions here or anything up to here?
Yeah, can you explain a bit? Sorry.
No, go ahead.
No, I just want to ask a bit about the intuition, because I still don't think I have like enough intuition why verification can be done so much better than simulation for this specific task.
Yeah.
Can you say a bit more?
Let's see. The intuition is something like this. So when we are trying to verify, we are essentially trying to solve a much simpler task. For instance, think of what happens in factor. So say I give you a very large number, and say you have some algorithm that maybe like you claim like factors it correctly, or like finds out the factors of that number correctly. Well, and then so what will like say you have this like process, and you like spit out maybe 2 factors of this number, and then you send them back to me. So how will I verify? So there are like 2 ways to verify. The first way to verify would be to like factor, like find out the factors of that number myself. That would be basically like mimicking the process that you ran, like to like find out the factors by yourself. Like so there could be the same process that I run on my device, like do the same thing. But there's a much simpler way of verifying. I could just divide the parent number by the things that you give me and see if and that is like a simple way to check if the number factor. So that's exactly why verification is much easier. So a priori for any task, simulation complexity and verification complexity can be extremely different. So there are these problems in NP, for instance, where this is the case. And
I agree in general. I was just asking specifically for this task of sampling. Can I think of the problem as being like some problem in NP, Like, is it actually the case that this is where the big difference comes from?
Exactly. So what we are trying to do, so I wouldn't say NP per se. So what we are trying to do, so these complexity classes are basically like worst case complexities. Like say I have some problem instance, I have like the worst case complexity is been captured by these classes. What we're trying to do is trying to design some average case sampling problem, which is in NP. Yes.
Okay,
That's roughly the motivation.
Thank you.
And so you can still run the circuit for a very short time. Can you, or just because of the fact that you have this separation between verification and simulation, it also means that you have to run this circuit for quite a long time.
Like the quantum part of the circuit is only run by the quantum computer, which the adversary has, and the verification part is fully classical.
Right, but you're saying
like
that verification can still be exponentially faster, right?
Yes. Verification can be much faster than classical simulation.
Oh, right. From that classical, right. Okay, right.
Any more questions? Okay, so let me keep proceeding. So now let me give you a sketch of the scheme. But before that, let me recap some very fast principle concepts from QEC. So any QEC protocol has 3 stages. The first stage is encoding. Here I have considered a simple bit flip code. And this is a logical one state of the code. There's some starting state. I have a network of CNOTs to prepare some code state of the code. So that's encoding. The second and third steps are syndrome measurement and decoding. So what's that? So say there's an error on the first qubit, say a bit flip error. So we first ascertain what happened, like where the bit flip happened, and by say the syndrome detection circuit, which I have drawn here. For the case of the bit flip code, the syndrome detection circuit is extremely simple. It's like just a mirror image of the circuit that I have to prepare the code state. And so I have this syndrome detection circuit and I have measurements in the appropriate basis. After I measure, I segregate the results into what I call Z syndromes and logicals. And the point is, the syndrome S will reveal what the logical L is. So basically, once we have the syndrome S, I can apply a decoding map D to reveal what the logical is. And the point is that the syndrome uniquely specifies the logicals. For instance, here the syndrome measurement will give you 1, 1. And if you refer back to the decoding table, this would basically mean that a bit flip happened at qubit 1. This is like simple QEC, like very fast principles. And now note something here. We can classically post-process the last part of the circuit. What does this mean? It means that first we can prepare this code state. There's a bit flip that happened on the first qubit, let's say. We measure in the complementary basis. And the point is, maybe we can measure right after the bit flip. We don't need to run the syndrome detection circuit and then measure. We can just measure. And now we can, after measurement, we get some samples. And now we can just use a purely classical map to map the samples to syndromes and logicals, and by some linear transformation. And this linear transformation will depend on what code we use. Did this scheme make sense? This is like just standard QEC. Okay. Any questions?
So then this is just like a standard quantum error correction task, right? You are
Just a
just
standard
preparing
task.
mistakes.
Yeah,
You're preparing some noise and then measuring. Okay.
exactly. Like a very standard thing. And the point is we can segregate the quantum part and the classical part very cleanly. And the quantum part can end right after that measurement. So now the point is, so my claim is that with errors or coherent errors, these schemes like QEC by its very nature will create a state that's conditionally peaked. What do I mean by that? I mean that after post-processing, we get an outcome L and a syndrome S. And basically, for QEC to work, for correction to work, the syndrome should uniquely specify like the logical error. So the point is, once we uniquely fix the fix the syndrome outcome, we know exactly what happened to the logical bit. And so in some sense, the logical is peaked, conditioned on the syndrome. So it's like a cartoon image of the state vector, like just for like demonstration purposes. This is not exactly the state vector, but think of it like this. So there are these syndrome blocks, and the logical outcome, the content of the logical is kind of unique with respect to each syndrome block. It has to be for QEC to work. By conditional peakedness. Any questions here? Okay, if not, so this is the key insight which we will use to design a quantum advantage experiment. How? So how can I use this insight to design a quantum advantage game? So let's play a game between Alice and Bob. So Alice now maybe samples a random code and an error channel. That's like say correctable by the code and gives the description to Bob, both the code and the noise channel. So Bob say prepares the logical plus state of the code, applies the noise, and say sends the samples back to Alice. And now Alice uses this peakedness to verify whether the right syndrome corresponds to the right peaks in the logicals. Let's unpack this, but before that, here is maybe Bob's circuit. So Bob has some starting state. So Bob knows what code, like Bob knows the code sent to him. So Bob prepares the logical plus state of the code. So the C0 network, after the C0 network, you have the logical plus state of some code. And you have errors now, like Z errors, like theta Z errors. So some of these pluses will be flipped to minuses. And now after this X basis, you will have some outcome, some like some sequence of say bits that you send back to Alice, and Alice will use the knowledge that she has of her code to now like fast apply the linear transformation to segregate those samples into syndromes and logicals and then verify whether the right syndrome maps to the right logicals. Did this rough scheme make sense?
Yeah, it makes sense, but I still don't see, for instance, sampling yet, right? Like,
right. I haven't gone into the details of say, yeah, like why things should be hard and yeah, things like that. But does it make sense why verification is easy? It's basically because like Alice knows what the code is. So once she knows what the syndrome is, she can map the syndrome to the right logical. And if it doesn't match, then she would know that Bob has cheated. And if it matches, then she knows that Bob sampled from the right distribution. That's the claim for verification. Any questions regarding this? Okay, if not, then the point here is this doesn't actually work. So this doesn't give you any quantum advantage. Why? Well, if Alice describes the code to Bob, then there's a very simple way to spoof the verification scheme that I just outlined without doing any quantum computation at all. So Bob knows what the code is. So Bob can just sample a random syndrome and use the code to map that syndrome to a proper logical. And so that spoofs the verification strategy that I just outlined. It's a very simple spoof. And so how do I fix this? The fix is kind of intuitive. And the idea is to just use two codes. So one would be to prove hardness of sampling, and the other would be to show that verification is fast. And we use CSS codes for this. We have, like, say, two binary linear codes, CX and CZ, and they satisfy some linear algebraic guarantees. And so CX is the secret code, and CZ is the public code. What do I mean by this? Well, Alice would keep the CX code and send the CZ code over to Bob. And additionally, let the error be e to the theta zi on all the n qubits. And the theta is chosen appropriately, satisfying some constraints. And so pi over 2, for instance, is a bad choice, but we'll go into that later. And what's the observation? The point is, for a CSS code, which has two components, CX and CZ, the logical plus state of say I have n physical qubits and k logical qubits. Like the logical plus state of the code on those k logical qubits is a linear superposition of all code words of the CZ code. And so to prepare this state, we do not need any knowledge of the CX code. Like the CZ code suffices. And that's exactly why even when Bob doesn't know the CX code, Bob can still prepare the logical plus state of this code. And then like measure and then sample from that. But why is Bob solving a hard problem? To address Shantanav's question, like why is it that Bob needs a quantum computer to do this? Well, one way to see this is if CZ is a worst case binary linear code, then we can actually prove complexity theoretically that sampling should be hard for classical computers. And how do I prove this? Well, and the underlying complexity theoretic conjecture is that we take for granted that the polynomial hierarchy doesn't collapse. And how do we prove this? Well, we prove using gadgets and post-selection. Note that the circuit we have is and we basically have C0 gates, like the circuit that I sketched out. The encoding circuit basically had a layout of C0 gates. And say we want to somehow turbocharge the circuit to have universal gate sets, like to have like T and Hadamard gates, let's say. Like once we have T and Hadamard gates, and once we can implement them wherever we want, we have like kind of like a gate set that can simulate any BQP circuit. And once we have a universal gate set, we can then, like I said, simulate any BQP circuit, which then can be, then there are like standard techniques to reduce that down to show a hardness of sampling result in the worst case. So the hardness of sampling part kind of reduces down to showing that we can construct such a gate set using post-selection. And we basically, yeah.
But Soumik, I agree that maybe using this you can show that that this is hard in the worst case, but I guess you would need average case, right?
Yes, exactly. And I will come to that in the next slide. And so that part is still a conjecture, but we have some evidence to justify that. Yeah, but just to complete the worst case chain of thought. So the challenge basically is that all the T gates are kind of in the last layer because of these theta zi rotations. And then we use post-selection to kind of lift them to different places of the circuit. And the gadgets we have are very similar to standard Hadamard and T gadgets that people use, say for measurement-based quantum computing. So that's the worst case hardness guarantees. But why is it hard in the average case? To answer Shantanava's question. But why do we believe that it's hard in the average case? So one observation is that the output probability of any string in our ensemble can be written in terms of the weight enumerator of the code. So more concretely, the output probability can be written in terms of like this polynomial. But theta is the rotation angle that we choose in the last layer, and x is the probability of the string that we are like looking at. And yeah, the theta comes from this like non-Clifford gate rotation angles. And what we know is that computing weight enumerators is sharply hard in the worst case. And this is another alternate proof of worst case hardness. And what we also know, or at least conjecture, is that computing the weight enumerator of a binary linear code, like a random binary linear code, like an average case instance, that should also be plausibly hard. A proof remains open. And the conjecture or the belief in coding theory is that the hardness should also persist for special families, like say much more structured codes, like low density parity check codes. Like computing the weight enumerator polynomial for most reasonable families of codes should be a hard task in the average case. But a proof of this would be quite interesting. Any questions here?
And approximating it is also like a conjecture to be hard, like
Yes,
to some relative error.
Exactly. Yes. The only family of like codes for which we know how to compute weight enumerators, I think is like Reed-Solomon codes. And anything beyond that, I think it's like so far at least it's not tractable. So any result here would be a breakthrough in like one direction or the other.
And the circuits that you would need, right? Typically for this scheme.
Yes.
How are they? Because it would you need a lot of qubits to
No, the
get some sort of
ballpark would be, I have some ballpark in the very like last few like the very like last slides, maybe like 120 qubits or something, it should probably suffice. Like and the point is you need to prepare some code state of the code. And so preparing a code state requires linear depth if you do not have like long range connectivity. So you either need like all-to-all connectivity, like for instance, you need to go to like Quantinum's hardware or like something like that. Or you need a lot of like, say like linear depth at least, if you want to do this in say Google's hardware or something. Okay, so this is the worst case hardness part. Let me now briefly talk about verification. So what if Bob is dishonest? So how are we ensuring that the verification protocol that we have is sound? So can we conjecture that the only way for Bob to output to like pass Alice's verification test, note that the test is still checking syndromes and like matching the syndromes to the logicals and seeing if there's a match. And now Alice uses her secret code to map the syndromes to the logicals, the code that Bob doesn't know, the CX code. And can we conjecture that the only way for Bob to spoof the verification test is by sampling from the true distribution? And the point here is this statement is false. So Bob can always spoof Alice's verification, like even without any knowledge of the CX code. Like Bob can still classically run a spoofer. So here's the spoofer. Bob can dishonestly replace all the e to the theta zi these rotations, these non-Clifford rotations, with Pauli Z errors, like Pauli Z rotations, just like Pauli Z gates. So the errors are of the same type. Both are like Z errors. So the peaks would be matched. Like the peaks would be matching. The peaks would be the same. But now the entire circuit is classically simulable as it is a Clifford circuit. So Bob can just classically simulate or sample from this circuit and have the syndromes matching the peaks. But there's a way to catch this spoofer. The point is that the syndrome distribution will be different. And the error can be written as, say, like a linear combination of, say, like I and Z, like with these theta weights. So after we measure, the syndrome distribution would depend on what theta is. So some benchmark that we define on the syndrome distribution will suffice to catch these types of spoofers. But before that, let me once again stop because I think I went a bit fast here and see if there are any questions. Did the spoofer make sense? The spoofer basically, so the key observation here is for Bob's circuit, if you go back to the picture of like the circuit that Bob is implementing, apart from this last layer of non-Clifford gates, the entire circuit is a Clifford circuit. And the reason sampling is hard is because of this last layer of non-Clifford gates. Like the reason sampling is classically hard. And what this spoofer does is that this spoofer replaces all these non-Clifford gates, like say, just like runs the Clifford circuit, like runs all the Clifford layers. And then for this last layer of non-Cliffords, the spoofer randomly picks either I or Pauli Z on each qubit in the end, instead of applying that theta zi rotation on the qubits. So then the entire circuit once again becomes a Clifford circuit, which is simple to classically sample from. And so, of course, the distribution will be very far in total variation distance. But the point is, the verification test that we have will not catch this difference. And how can we modify the test to catch this difference? The point is,
so, Soumik, sorry to interrupt you. So the reason that you won't be able to catch is precisely because the peaks are happening at the same point. Is that why?
Yes, exactly. Yes, the peaks are at the same point. Exactly.
Okay.
And the difference though is that the syndromes are different. The syndromes are coming from a different distribution, but the peaks are happening at the same point. Any more questions? Okay, so now the point is we somehow need to test the syndrome distribution. Just testing for the peaks is not sufficient. And so somehow we need to verify the syndrome margins. And so what do? We basically, the point is if we somehow verify the syndrome marginals and we also verify the peaks, that should suffice. That should suffice to like certify that like Bob is honest. And so you somehow need to check the total variation distance closeness to the syndrome distribution. Like we need to ensure that Bob is sampling from the right syndrome distribution. But total variation distance is not sample efficient to test. So we use a proxy. And we use something very similar to linear cross entropy. And we conjecture that the test we come up with is hard to spoof. We call this the red test, the relative cross entropy difference test. So given k samples, we basically compute a figure of merit. And so this Q reference is any efficiently classically sampleable distribution. Like say it could be this Pauli spoofer that we just outlined. This is how, for instance, so I won't go into the details of this test, but this is how people verify boson sampling, for instance. And a high positive score implies that you are close to the ideal distribution. A negative score means that you are like close to the spoofing distribution. There could be many other tests. This is like one example of a particular test that we can run. But why is verification faster than simulation? We are still doing some linear cross entropy test. So why is it that verification is faster? So the point is the syndrome distribution by a fact from QEC, by the Neel-Laflamme theorem, does not depend on the logical input state. So the syndrome distribution only depends on the errors alone. And this can be proven by the Neel-Laflamme theorem. So the point is, so once we have the syndromes, verifying the peaks is easy. So now verification reduces to just verifying the syndrome. So when we just want to verify the syndrome, we can consider a much simplified circuit. We can set most of the input qubits to 0. We basically, instead of preparing the logical plus state, we can prepare the logical 0 state. And that should still suffice. So all the qubits, except for the X syndrome qubits, the syndrome qubits for the CX code can be set to 0. And so the stabilizer rank of the state that we are simulating to simulate the syndrome marginal will drastically go down. It just depends on the number of X syndrome qubits. So we can compute statistics of the marginal distribution of the syndrome just by simulating this like in time that's proportional to this. And that's exactly where the saving is coming from. It's still exponential because we aren't getting rid of linear cross entropy, but we are applying linear cross entropy on a much smaller sub-circuit. And then we are looking at, say, the logical register. Then we are like doing a peak verification subroutine on the syndrome to check for the logicals. And that's the verification task. Did this make sense? Okay. So the verification time is greatly reduced because the stabilizer rank of the state that we use to keep track of the syndrome marginals it just depends on the number of syndrome qubits. So the dominating cost comes from syndrome verification because once we have the syndrome, verifying peaks is polytime. This is much faster than simulating the entire circuit. And the ratio between these two times can be made, like say simulation time and verification time can be made very large. And now some concrete numbers, as Shantanamata was pointing out. So we need 3 desirable properties. We need fast decodability. Why? Because we need a linear transformation to map the syndromes to the logicals, which is basically applying a decoder. You feed the syndrome to a decoder and see what logical comes up. So we need the decoder to be fast. We need high distance because note that we have like errors that are kind of like linear. We have n like theta zi rotations. So like, yeah. So if we have high distance, we should be able to correct for most of these. And that's desirable because if you do the math, so the distance kind of factors into the weight of the peak. In practice, or like when you work out the math, the weight on, say, the right logical will not be 1 given a syndrome. It will be like 1 minus some negligible fraction, where a lot of like things need to be kept track of. Like a parameter that determines how much weight we can put on the beak is the distance of the code. And we also want the code family that we have to have like good hardness guarantees. Like we can't pick a Reed-Solomon code, for instance, because their computing probabilities is easy. So we need these 3 properties. And we also want NISC friendliness. So we want the code to be implementable in whatever hardware we care about. So LDPC codes should suffice. There are codes like Gallagher codes that should also suffice. And there can be many other code families. And like I said, if we want to put numbers, maybe 120 physical qubits, and maybe the syndrome length is 30 or 40. So which basically makes the simulation time 2 to the 120, but verification time 2 to the 30 or 40, depending on the number of syndrome qubits. And what are some open directions? Well, we want experimentalists to implement the scheme on hardware. So that's one. So making these parameters like trying to find out what code angles or like code parameters or rotation angles make our scheme competitive. That's one. Other directions? Well, note that one nice feature of this scheme is that one part of the code is private, the CX code. The other part is public, the CZ code. So then can we get something like public key cryptography from this primitive or from these types of circuits? So because this is exactly the type of duality or the type of asymmetry where public key cryptography, which can be leveraged to get public key cryptography. So another thing is, how well does our scheme behave under noise? Can we analyze what? So we only analyzed like noise that we ourselves introduce to the circuit by these theta zi rotations. But there could be many other sources of noise when we are actually preparing the code state. We haven't factored those in. And how well does our circuit behave under noise, and do spoofers work in this noisy case? And can we have a better justification for average case hardness? I think from the perspective of a theorist, this is the most important open question. Can we maybe, for instance, to start with, can we show that for a random binary linear code, computing weight enumerators is sharply hard? It might be easy to show this up to some precision. Maybe people just haven't tried it. And thank you.